All right, so last time we were working in section 1.2, and we were talking about this new idea, at least in terms of a new idea that calculus brings about, this idea of limits. And as we were taking a look, we had taken a look at one example where we compared a graph and what the limit would look like from a graphing standpoint to a numerical standpoint, and we found that they gave us both the same value. And we talked about why they sort of went together and why that made sense. Does everybody remember this? The other thing we talked about on this one is we talked about sort of the why in the world does this happen, and that is to say, why does this sort of look like a line, and this equation didn't look like a line, and we talked about the fact that it has some properties where we can actually do some factoring and some simplification, which we'll get into in 1.3, but I want to show you that when that factoring and simplification does not occur, things can vary quite differently. So we're going to take a look at this equation. Go ahead and grab your calculators and put those in. We didn't actually do this one in class, right? Okay. So I'd like for you to take your calculator. I'm going to be over here on the screen. I know it's against the chalkboard, but in fact, I'll move over here so you guys can see better. And so in y equals, we're going to put that equation. You make sure you put it in parentheses if your calculator doesn't have the division set up so that it looks like the pretty math type, because some of you have that set up. If yours looks like mine, you will have to put the top in parentheses and the bottom in parentheses to make sure that your calculator is understanding what in the world is dividing. It's dividing the entire top by the entire bottom. And then last time you should have also had the table set up so that if you went into the table, we actually still have those same values from last time. Are we all good so far? Now remember, the reason we chose those values is because those values are very close to the value of 3. The first ones of them, 3.1, 3.01, 3.001, are slightly larger than 3, and then the other 3 are slightly smaller than 3. And as we're working in our table, we'll use those same values in our table. And of course, if we plug in 3, we're getting the calculator to say error. And why was that happening? Because a 3 would put a 0 in the denominator, right? And we can't divide by 0, so our calculator just says error when we try to do that. All right, so we're going to actually write in these values. These y values are wonderfully all set up for us and everything. So we can put in here that the y value comes out as 186.1. Now, I mentioned last time that if you wanted more decimals, you can arrow over on top of that value. And you can see along the bottom of the screen right here what, down here at the very bottom, what the value actually is, either in its complete form if it stops, or if there's simply more decimal places we can't see. So you can go in and you can fill in those values more accurately. So we have 1806.01, then I have 18,006.001. All right, the other half of my equation, or the other half of my values, I have negative 174.1, negative 1794.01, and negative 17994.001. They actually all terminate. All right, so we're going to compare the two tables that I have set up. As you're going down this table, what's happening? They're getting bigger, and they're getting basically about 10 times bigger each time, right? Because I'm actually adding an additional number to the number, how long the number is each time. So this is getting infinitely larger. So if we expected, or if we tried to do 3.0001, if we added another line to the bottom of our table, what would our expectation be in general? We would get just a bigger number than we even got right now, right? Now, we're going to talk about this in a little bit different way later, but right now, the basic idea is that this is getting infinitely large. It's going to infinity. Okay? And again, we talked about this last time too, but just as a reminder, what this table does is it's the limit as x approaches 3 from the right, because these numbers are slightly larger than 3, of our function. We'll call this function f of x. So this, I'm giving the name f of x to match this. The other table takes the limit as x approaches 3 from the left, because the numbers are slightly smaller than 3. And take a look at this table. What happens to that table? It gets bigger, but negatively, right? I get negative numbers, but they still are getting increasingly larger. So if we sort of look at this the same way that we did on the first table, what would this value be sort of approaching? Negative infinity. Now, we talked about last time, and I'll go back to the slide where it says it, this idea of limit existence. And we said a limit exists if and only if both corresponding one-sided limits exist. And we can talk later, and we will talk later in section 1.5 about whether the infinities, we should call them as being existing or not. But it also says that not only do they have to exist, and we can argue about that, whether these exist or not, but it also says they have to be equal. And we don't really have any chance to argue that one, right? I mean, are these equal? No. So even if we say infinity is a value that we call existing, and we may do that once we get to 1.5, they still aren't the same, right? One of them's positive, the other one's negative. So on this problem, this limit, as x approaches 3 of this function f of x, does not exist. Because the corresponding one-sided limits are not equal. So we're going to look at a picture of this and try and figure out why in the world all we did between problem number 2 and problem number 3 is we changed the sign on the top. In problem number 2, the sign on the top said x squared minus 9. This one says x squared plus 9. Why in the world would such a small change actually result in such a different outcome? So we're going to start to address that issue by taking a look at what the graph looks like for this. So because we haven't graphed together yet, I want you to hit the window button over here. And yours may not look like mine. So we can do one of two things. We can either each go in and make sure all of our values look the same, or we can do a zoom feature that will make them all look the same. I'm going to suggest zoom. I want to hit zoom, and we're going to choose number 6, which is a standard viewing window, which is a negative 10 to 10 viewing window for the x values and the y values. Do your graphs look something like this? Does everybody have that sort of straight vertical looking line on theirs? Not everybody probably will. Some of the calculators are more advanced and deal with this a little bit better. I'm going to zoom out because I'm only seeing the left-hand side over here. I don't see anything happening over here, and I know something happens over here because I plugged numbers in and it worked. So I'm not seeing those values, so I'm going to zoom out to make sure I can see those. So I'm going to hit zoom, and it's number 3 to zoom out. And then if I hit enter on this screen, it will do the zooming out. Again, not all of your calculators are going to put that straight vertical looking line there because the reality is it's really not there. It really isn't. Where do you suppose that vertical line is showing up, though? It's at 3. So before 3, and this is just, a rough picture of what's happening, it looks something like that. And after 3, we've got it looking something like this. And at the number 3, what your calculator is actually doing is it's trying to connect the top piece that's really high with the bottom piece that's really low, and it's doing so with a straight line. The line's not really there because what really is there? A what? It's not a hole. It's an asymptote on this one. So we're going to talk more about asymptotes again when we get into section, I think it's 1.4 or 1.5. But there is a vertical line right here that's an asymptote. It's a line we're going to get really close to, and in this case we're not going to touch it. And the reason we can't touch it is because we have no input value for 3, because 3 would make this function in the denominator 0, and it would not exist. So on the last one, when I had that x minus 3 in the denominator, it had the ability to cancel out with something in the numerator, and that resulted in a hole in the graph. On this one, that numerator doesn't actually factor. So since it doesn't factor, it doesn't reduce with the denominator, which means that that x minus 3 can't go away. So it will represent having an asymptote on our graph. Now you can see on this particular graph, if I start to the right of 3, which is this over here, and I move toward x equals 3, if I talk about doing the limit, what's happening? It's getting infinitely larger, right? That's where this infinity came from down here. And if I take a point to the left of 3, and I move toward x equals 3, what's happening? It's getting infinitely smaller, which is why I'm getting the negative infinity down here. So there is a direct correlation or direct connection between these numerical charts we're creating and the graph and how they relate to one another. Okay, does this make sense? Okay, we've got one more example to do in this section. We won't need that again today, actually. All right, last example in this section says that we are going to, or we're supposed to, sketch a graph of a function with the given properties. Now, this is one of those questions, I really like these kinds of questions, because Nikki could find and create a picture for this that looks very, very different than Jamie, right? Than Jamie does, and they could both be correct. And that's kind of cool, because that doesn't always happen in math, right? In fact, some of you really wish it weren't happening right now. You're saying, say what? Math's supposed to have one answer, and she just told me it might have more than one? Well, on this one, the answer is yes. Now, there's some features about their graphs that would have to match up, but there are some features that would not have to match up, and they still could both be correct. So the first feature is the feature that's going to be the same on all of our graphs. What does this piece of information tell us about our function? What does f of 0, 1 mean? Say again? Not going to, because that's an idea of a limit, and there's no limit on what's encircled in green. That notation that's in green you've seen when you did up like a college algebra or an algebra 2 in high school. What does f of 0, 1 mean? It's actually a point. It's a point on the y-axis, so it's the point 0, 1. It means that on our graph, we are all going to have a location, part of our graph, at 0, 1. So you've got a point somewhere like that. That's part of my graph. I'm going to draw my graph in red. Now these other two pieces of information are going to do what Micaiah was referring to, this idea of getting close to something, because they've got that limit notation in there. So what is that limit with the value underneath it? What does that mean? Somebody say that correctly mathematically. What does that notation say? How do you read it? Okay, so this is the limit as the function is approaching x equals 0, right? From the left. Sorry, I shouldn't have said right, I should have said correct. X equals 0 from the left. So I'm starting somewhere over here. I don't know, I'm starting somewhere over there, and I'm supposed to be getting close to the x value of 0. So I'm moving from this way over to the x value of 0, but what value am I supposed to be getting close to? 2. So I'm supposed to be getting close to here, right? But here's where you've got freedom to do what you like. You can draw anything before that circle as long as you end up at the circle when you get close to x equals 0. So maybe you draw this. Maybe you draw that. Maybe you draw this. You can draw anything you want. It just has to end up at that open circle, because from the left-hand side, tracing along whatever you put on the left side of the graph, you've got to be getting closer to a y value of 2. What are we going to do on the right-hand side? We're going to get close to a y value of 3. So we've got the open circle at 3. What do I have to draw on the right-hand side of the graph? Anything I want. That's right. I do need to draw something, though. I mean, I do have to draw something. So I'll draw that. And it has all of the features that I was given, and my graph does not have to look like yours. It's kind of different, right? You're going to get to do at least one of those, or maybe 2 of those in your homework, I can't remember, where there are some features, your graphs, that are going to match, but there are some features where you have flexibility too. Any questions on that one? All right.